Alright guys, here we are, concept 53.3. This one is all about the logistic model of population change, and this is probably more accurate, the one that you see more often in the real world. The logistic model describes how a population grows more slowly as it nears its carrying capacity. So we'll want to define what carrying capacity is, and then we'll see how that population growth that we saw just a minute ago, the exponential growth, can't occur and go on forever because of the carrying capacity of a particular area. So let's discuss that just a little bit. This is the more everyday model that you see, the more likely model that you're going to see concerning population growth in a group of living creatures. While we said that exponential growth was basically in a place where there were no limitations, no limiting factors, unlimited food, or no predators, something like that, and it was growth that grew along with the population. In other words, it got faster and larger and faster and larger. That cannot be sustained for long in any normal population. A more realistic model limits growth by incorporating this idea of carrying capacity. We're going to use the letter K to represent carrying capacity, and that's the maximum population size that any particular environment can support. And the carrying capacity is determined by a number of factors that would include living and non-living biotic and abiotic factors, predators, and weather conditions, and food supply, and space, and the like. Carrying capacity varies with the abundance of limiting resources. So again, some mathematics here, and I want to stress the fact that I wouldn't ask you to memorize the formula that you see below, the expression that you see. I really want you to understand the idea or the concept behind the formula that you see. In the logistic population growth model, the per capita rate of increase declines as carrying capacity is reached. So remember, we had that little letter R, which was basically the rate of increase, the difference between births and deaths. And what this says is, as you get closer to the carrying capacity, this rate is going to decline. It's going to go down. The logistics model starts with the exponential model, and it adds in an expression that reduces per capita rate of increase as n approaches k. So basically, we would look at the exponential model, but we add in this portion here that shows the reduction in r as you get closer to k, which is carrying capacity. And again, I don't want you to think you have to memorize this or know this from memory or just spit it out at will. I just want you to really know the background, the concept behind this. So in other words, the closer the population gets to carrying capacity, the more its growth slows, and the smaller and smaller the difference between the birth rate and the death rate. Here's a table of figures that would show logistic growth of a hypothetical population, and they are saying that K, or carrying capacity, in this case is 1,500. So the maximum number of individuals of creatures that this area could support is 1,500. We're going to start out with a population size of 25, and we're going to go all the way up to that maximum carrying capacity of 1,500. Now what we want to look at are a couple of different areas here. The per capita rate of increase. Notice how this drops as we get closer to the carrying capacity. This is the rate of growth. How quickly are we growing? So it is dropping as we get closer to the carrying capacity. Now the actual number, the population growth rate, continues to rise because the group is getting larger and larger, so that means there are more and more reproducing members of the group, but the rate of increase is going down. So yes, the population is still rising. We're getting more and more of the creatures until we hit 1,500, but the rate at which we increase is dropping as we get closer and closer. So this idea of logistic growth is right here in this column, where yes, the population may continue to grow in size until you reach carrying capacity, but it slows down that growth in size. Think about it like in physics, where you're talking about acceleration. You can accelerate quickly or you can accelerate slowly. You're still speeding up, you're still gaining speed, but you can do that in a faster fashion, like up here, or you can do that in a slower fashion, like down here. Either way, the population is getting bigger, but this describes the rate of growth, and it shows how it slows the closer you get to the overall carrying capacity. Just like we did with the exponential growth model, we could also look at this in a graph. In a logistic model, if you put that on a graph, it shows a sigmoid or S-shaped curve. So in this case, we have the exponential, which is the yellow line, and we have the logistic growth, which is the S-shaped curve line. So you can see how our growth begins to level off as we get closer to the maximum carrying capacity of that particular area. Another example of the same thing. So we have the exponential growth where the rate of growth continues to rise, and then here we have the sigmoid curve where in logistic growth the population growth begins to slow here, and so instead of a steady uprise, it's still rising, but it begins to taper off, and so the rate is beginning to slow as we continue on. The book does a good job of giving you some real-life examples of where you can see the logistic model in real populations. One of the examples I give is growing paramecia in a laboratory population. Fits a nice S-shaped curve. If these organisms are grown in a constant environment, lacking predators and competitors, if they have pretty much everything they need, and they don't have to fight for resources, well, they will eventually take on this S-shaped logistics model where their population will rise. But then as they reach carrying capacity for that petri dish or whatever environment they're in, the population rise will continue, but it will go at a slower pace until it will begin to level off when they reach the carrying capacity. Sometimes it's not a nice smooth S-curve. Some populations tend to overshoot K, which is the carrying capacity, before they settle back down to a relatively stable density. So you can see that in a couple different populations as well. They give you another good example of these water fleas, which are called Daphnia. And again, if they're put in the same situation where they have a nice stable environment, plenty of food, no predators or no competitors, they will actually overshoot the carrying capacity, and then they'll have sort of a die-off. So you see this curve going downward, which means they have actually more deaths than they do births. So their population is dropping until it comes back to that carrying capacity, and then it becomes fairly stable over time. Of course, in biology, things are not always just cut, clear, dried, and simple. There is something called the Ali effect, which we'll talk about, which makes some populations difficult to measure because some populations fluctuate greatly up and down, and they make it hard to determine what the carrying capacity is. They tend to overshoot the number that you would think would be the carrying capacity, then they fall under for a great amount of time, and so it's sometimes difficult to define what the carrying capacity is. And then there's something, like I mentioned, called the Ali effect, named after W.C. Ali of the University of Chicago, who first described it. And this is a model that shows that sometimes it's more beneficial to have more creatures. Most of the population models we've looked at assume that each additional individual has kind of the same negative effect on population growth. In other words, adding an individual helps to slow the population growth once you get close to carrying capacity. But some populations actually show that there's a benefit to having the larger population. Single individuals might have a worse time off surviving than groups of individuals, and so if that's the case, it would tend to sway this carrying capacity number, and it would make it difficult to determine. A good example they give in the textbook is if you have a single lone tree, well, it might be more apt to be damaged by, say, wind or storms than if you have a bunch of trees in a forest or all grouped together. There may be some benefit to that group to protect some of the trees from wind and storm damage and the like, and that would be called the Ali effect, to where the addition of an individual doesn't necessarily slow or have a negative effect on the population growth. And that's going to be only up to a point, because eventually you are going to reach carrying capacity, and then each extra individual is going to be problematic, is going to have a negative effect. So these are some of the things that can cause this not to be clear and cut and dried, which is often the case in biology, of course. Just like we mentioned with the exponential model, while the logistic model is more accurate and more realistic, doesn't mean that that perfect S-shaped graph is going to fit a lot of real populations. There's too many variables that have to be measured and taken into account, and so out in the real world most populations don't fit either one of these models perfectly. But particularly the logistics model is useful for kind of estimating possible growth and for looking at things like endangered species and the like, and for estimating how that population is going to change over time. So conservation biologists can use this, for example, to estimate the critical size below which populations may become extinct. So for example, when we talk about the polar bears and how the population of polar bears has steadily declined in the last, say, 50 years, well, they're eventually going to get to a point where it will be almost impossible for that species to recover. Same thing like with the rhinoceros, this white rhinoceros. Some of these species, when they are endangered or threatened, their population will drop to a certain level to which basically there's no turning back. There's almost no way naturally for them to recover because the population density is so low, and because some of the reproductive issues that they faced in finding mates and having habitat, It's almost like a point of no return. If you were talking about astronomy, you might consider it the event horizon, where you can't come back from. And so population ecologists are very aware of these numbers, and they take a lot of information to put it together to try to warn us, society, about these particular instances. Alright, we're going to take a break. So that is the logistics model, which is probably the more realistic, more accurate model, the one that has to do with carrying capacity, which is a little bit different from the exponential model, which was like the model of population growth if you're talking about no predators, unlimited food, unlimited everything. Those are the two main models. We'll come back with concept 53.4, which talks about life history traits being the product of natural selection. So how much the rate of reproduction and population density and all these various things that we've been talking about, they are all related, of course, to evolution and natural selection. We'll discuss that coming up in the next concept.